There we go. Okay, so like I said, we are covering 6.1. And this is on the inner product, length, and orthogonality. Okay, so we are going to define all of these things. So the first thing is to define the inner product, which we will more often refer to as the dot product, but you can use these interchangeably. And this is a way of sort of multiplying two vectors in a particular way. So the inner product of two vectors, u and v from Rn, is going to be, so this is denoted with a dot between them. That's why we refer to this as the dot product. So u dot v is going to be equal to, remember these are both column vectors, so it will be u transpose times v, where we just multiply these like matrices. So that would be u transpose would turn this into a row vector with entries u1 up to un times v1, v2 up to vn. Right? And then we just do regular matrix multiplication, which in this case will give us just a number, right? So we would get u1 times v1 plus u2 times v2 up to un times vn, right? So what happens when we take the dot product of two vectors is we get a scalar, we get a real number, right? So that's important. The dot product or inner product of two vectors gives a scalar, not another vector, right? Right, a real number. Okay, so let's just do a quick example. If u is equal to 1, 2, 3, and v is equal to 4, 5, 6, then u dot v is going to be where we just take each of the entries. So we multiply the corresponding entries. So we'll multiply 1 and 4 together, and we add that to the second entries multiplied together. So 2 times 5. And then lastly, we have the last entries multiplied together. So 3 times 6. And then we add all of this up. So in this case, we get, this is 4 plus 10 plus 18. So that sums to 32, I believe. Yeah, so this is how we compute the dot product. And we have some properties, which we won't verify. We will just state them, but these will hold. So if you have vectors u, v, and w in Rn, and a scalar c from R, then we have the following. We could take the dot product of u times v, and that would be equal to the dot product of v times u. So it doesn't matter what order we do this in. We can distribute. So if we have u plus v dot w, that is the same as u dot w plus u dot v. And then if we multiply by a constant times u, then dot with v, that's the same as first dotting u and v and then multiplying by a constant, or you could multiply v by the constant and then take the dot product. So it doesn't.
Pardon me.
Yeah.
I'm not sure about the second property.
Mm-hmm.
It says that so the vector u plus v times w. Oh, do you see it?
Yeah, w. Right.
So that would be v times w.
Oh, geez, I was all over the place. Yeah.
Okay, cool. Making sure.
Okay, yeah. Thanks. Yeah, that's definitely true. Okay, so we have this property. Okay, cool. Okay, so we have these three, and then also if we take v dotted with itself, this will always be something greater than or equal to 0. Sort of in the same way where if we take a real number and square it, it will always be greater than or equal to 0. We have the same behavior here, which you could check by just writing out what this is. Okay, and furthermore, if v dotted with itself is equal to 0, if that actually occurs, then we must have that v is the 0 vector. In fact, this is the only possibility. So v dotted with itself is equal to 0 if and only if the vector v is just the 0 vector. Okay. So this means that when we're taking the dot product of v with itself, what we can do is basically assign a number to it. So it's sort of like for every vector, we can take v dot v. And the only vector that gets assigned 0 is the 0 vector itself. So this kind of sounds like a length, right? So it is actually related to the notion of length, right? And so we can have the following definition. The length or norm of a vector v in Rn is going to be, so we'll denote this with these double lines. So it kind of looks like an absolute value, but you have two lines, right? This is going to be not just v dot v, it will involve v dot v, but we're going to take the square root of that, right? And if we write out what this is, we get v1 times v1 plus v2 times v2 up to vn times vn. Maybe I shouldn't put dots in between these because that's confusing. Okay, so this is just regular multiplication because these are real numbers. And the square root. So that's v1 squared plus v2 squared plus vn squared. Okay. And so if you look at this in R2, so if v is just a vector in R2, you get that the norm of v, or the length of v, is v1 squared plus v2 squared, right? So it agrees with our notion of length that we already have, right? So this is just the distance formula in R2, right? And if this is our vector v, and we know that this would be v1 and v2, then the length is going to be the square root of v1 squared plus v2 squared. Okay. Okay, so this is our definition. This is how we will do this. And one thing to note is that if we take v and multiply by a constant, and then we want to figure out what the norm of that would be. Okay, so how does this differ from the magnitude of a vector? This will be the same as the magnitude. Yeah, so I guess you could also call this the magnitude. Unless, I am not sure, maybe, I don't know if magnitude includes like negative numbers. This definitely cannot be negative, right? Because we have the square root of something, so. But
yeah,
if,
no, it seems to be defined the same way. It's just a slightly different notation, and I just wanted to make sure.
Yeah. So I think it would be, yeah, the same thing.
Okay, thanks.
Cool. Right. So, right, if we're looking at v times a constant, we can write out what that would be. That would be c times v dotted with c times b, right? And then by our properties that we just stated for dot products, we can pull those constants to the front and group them together. And so this will be the square root of c squared times v dotted with itself. And then we can split this square root into the square root of c squared and the square root of v dot v. So this is just the norm of v, right? We just define that. So here we have the norm of v, and then this is going to be the absolute value of c. So if we take a number that may be positive or negative, and we square it and then take the square root, what we get is the absolute value of c, right? So this means that the norm of c times v is equal to the absolute value of c times norm of v. So this is absolute value when we have just one bar, and when we have two bars, that's the norm of a vector. Okay. So we can not only define the length of a vector, but we can also define the distance between two vectors. So if we have two vectors u and v and Rn, then the norm of u minus v, so if we take the difference of those two, this is going to give the distance between them. And if we want to visualize what's going on here, so if we had two vectors, we'll just say they're in R2. So it's easy to draw. So we have u and v, and the vector u minus v is going to be, or sorry, I guess, oh yeah, if I draw it this way, this is u minus v, right? That one right there. See that gives the distance between those two vectors, really the endpoints of them, but so we can see that the distance between u and v, so we'll just denote that this way, is going to be equal to the norm of that pink vector, so it's u minus v.
That looks like a lot like a triangle, right? In which you could use like a lot of cosines.
Yeah, exactly. How the vector u minus v works. Oh, well, you could just translate it to the origin, right? So you can just think of this vector as being like displaced, right? It's just translated.
I'm sorry, I still don't really understand it. Like,
So
how do you get it? What does it mean that it's that? How does it become that distance between the two?
right. So the idea is, so we have u and v, and u minus v is going to be, let's just draw this in a different color. So minus v would be the same, in the same direction as v, but no, well, it will be in the opposite direction of v and the same length, right? So this would be minus v. And if we want to add these together, we could, I guess, do this tip to tail thing. So translate it to up here. And then we get this vector. I'll just do like this. Right there. That would be u minus v based at the origin, right? But it would, you can just imagine like translating it over here. So it'll be that vector with the same length. And it's just convenient because we have this like parallelogram picture for adding vectors, right? Where we get this guy, and this will be u plus v here. And then u minus v would be this vector here just translated so that it starts at the origin. So if you don't like thinking of it this way, you can think of it this way. Okay. Okay, so we have this distance formula now, right? Okay, and then since we have this notion of length, we can define a unit vector. Which will be a vector of length 1. Great. Okay. And given any vector, actually any non-zero vector, in Rn, we can find a unit vector in the same direction by dividing by the norm of v. So our unit vector will be v divided by the norm of v. Or you could think of this as 1 over the norm of v, which is a constant, times the vector v, right? So whatever length your vector was, we just scale it to then be just length 1. Okay. Okay, so now we've covered the inner product, the definition of length, and then the last thing we want to define is orthogonality, right? So here, the idea of orthogonality is like extending the idea of like right angles in the plane, right? So we know that, well, we know how to define that in the plane, but we are going to use the dot product to define it in higher dimensions. So two vectors, u and v in Rn are orthogonal, or you could say they're perpendicular if u dot v is equal to 0. Okay, now why do we use this definition? Well, if we're in the plane and we're looking at two vectors, u dot v, we can show that we get the following formula. So u dot v is equal to the norm of u times the norm of v times cosine of theta, where cosine of theta is going to be the angle between the two vectors. So if we have u and v, theta will be that angle there. Okay, so if this is the case, if we're assuming this, which we'll get to in a second, showing why this is true, but if we do have a right angle between those two vectors, so if theta is equal to pi over 2, then cosine of pi over 2 is 0, and we see that u dot v is equal to 0. Right? Okay, so then this sort of gives a motivation for this definition, which is going to work in higher dimensions than just R2, right? And then let's talk about y. So y is u dot v equal to norm of u times norm of v times cosine of theta.
Is this like a general statement which you use for a specific angle, which is pi over 2, show that dot product is equal to 0?
Yeah, yeah. So this, yeah, holds in general for all kinds of values of theta, but yeah, when theta is equal to pi over 2, we get that it's 0. The dot product is 0. Okay, so we can justify this using the law of cosines, which you may or may not remember, but it does say that the norm of u minus v, well, in our notation using norms now, that the norm of u minus v is equal to the norm of u plus norm of v, norm of u squared plus norm of v squared minus 2 times norm of u times norm of v times cosine theta. So this is the law of cosines.
Where did you get this, the law of cosines thing from? This looks completely like, it looks unfamiliar to me.
Right, so it basically comes from like Euclidean geometry, right? So this is something like akin to the Pythagorean theorem, which can be proven a lot of different ways, but it's sort of not, I don't know, essential to this class. So I'm just kind of like assume that this is true and it can be proven. but we will not do that. Okay. Right, yeah, they're like fun little proofs of that. Okay, so assuming that this is true, we can see that we've got what we want on this side. So let's do some manipulation. So if I pull it over to the left-hand side, it'll be positive. We get u times v times cosine theta equals, now we get norm of u squared plus norm of v squared minus norm of u minus v squared. Right. And then if we write out what this gives us, so we're in R2, so we're just dealing with vectors with 2 coordinates, and this will give us, so we'll divide by 2, and then we can write out what this would be. So we'll get u1 squared plus u2 squared from this first piece. Then we'll get v1 squared plus v2 squared from the second piece, minus u1 times v1. Oh, no, sorry. u1 minus v1 squared plus u2 minus v2 squared. And then, right. And then you can multiply this out and you get a bunch of cancellation, turns out. And you should get 1/2, 2. So I'm not going to do that part, but you should get 2 times u1 v1 plus 2 times u2 v2, which gives us u1 times v1 plus u2 times v2, which is just u dot v.
So is this proof for why the equation works? Is this only for R2?
Yeah, it is in R2. Basically, this works in R2, and I guess it's a little bit more complicated in R3, but for higher dimensions, we use this almost like as a definition of what it means to have an angle theta between 2 vectors. So in higher dimensions, we say that the angle, we say that, yeah, okay, sorry, I forgot where I was going with this. The angle between U and V is theta satisfying this equation. So we just do U dot V over norm of U times norm of V.
Is there like a specific name for this formula?
Not that I know of. Maybe. Yeah, I don't know. But basically, this gives us a good way of defining the notion of angles. So all we needed was the definition of dot product to define an angle between 2 vectors, right? Okay, so this was all just to motivate this definition, which by itself doesn't seem very intuitive, right? But so we just say that 2 vectors are orthogonal if their dot product is equal to 0. Okay. So one thing to note is that zero is orthogonal to everything. right? So it's orthogonal to any vector v in Rn, since 0.v will give you a sum of a bunch of zeros, so this will be 0. Okay, so here are some inequalities that probably won't come up, but are kind of interesting that you can verify yourself or look up. Actually, I think this second one might be a little difficult to prove. I think there's like some kind of trick here. So the triangle inequality says that the norm of u plus v is less than or equal to norm of u plus norm of v. This is very useful in a lot of math. So we have that. And then we also have the Cauchy-Schwarz inequality, which says that the absolute value of u dot v is less than or equal to the norm of u times norm of v. So remember that u dot v gives you a number. So this is just a regular absolute value of that number. Okay. And yeah, so these are just good to know. But like I said, probably won't come up for us. All right, so next we can talk about a vector being orthogonal to an entire subspace. And so we'll have a definition of this. So a vector V is said to be orthogonal to a subspace W if v dot W is equal to 0. So if it's orthogonal to every vector W in W. Okay, let's see. Okay, so if you're having trouble with orthogonality, maybe you could think like perpendicular, like maybe that feels like more comfortable. So you already know about like, lines being perpendicular in R2, and maybe you could imagine that extending to R3, right? Yeah. Okay, so we have this definition. It is orthogonal to a subspace if it's orthogonal to every vector in that subspace. So it's kind of a definition that makes sense, right? And then we also can define what we will call the orthogonal complement. So if W is a subspace of R, of Rn, the orthogonal complement of W is going to be the set. So we use this notation. So this sort of notation that we usually use for perpendicular lines, right? So it would be the set of V in Rn such that V dot W is equal to 0 for all W in W. So we're taking all, like the collection of all of the vectors that are orthogonal to W. And if we stick them all together, into one set, that's what we call the orthogonal complement. Okay. So this is red W perp, or W perpendicular, but usually we just say W perp. Okay. And maybe let's have some pictures of what this looks like in R2 and R3, which might help us understand what this is saying. So we have in R2, a non-trivial subspace would have to be a line, right? Otherwise we would have just 0 or the whole space. So if our subspace looks like this, say this is W, then the collection of all vectors orthogonal to this will be just the vectors on this line. Oh, okay, try to make it nice. Great. So we have a right angle between those two. And if we take those all together, that will form W perp, right? And in R3, I will try my best to, okay, we're gonna just do without the axes. Okay, so say we have that our subspace is a plane in R3, then our W perp will be a line okay. So it'll be this line right here. Does that make sense, what I'm trying to draw?
It makes more sense.
Okay.
I guess I'm struggling with it because it's almost like what I thought was perpendicular.
Mm-hmm.
And like I thought perpendicular was like a concept, and it turns out perpendicular is almost like a smaller part of the larger concept of orthogonality.
Right.
Right.
Yeah.
Which hurts my brain.
Right.
Like I read orthogonal and it doesn't really mean anything to me. I'm like, that's a word, but it doesn't like, so I'll work on that.
Okay. Okay, so we can see so these are two examples of W perp just drawn out. So this would be the 0 vector right here, just so you. Maybe you could guess from these pictures, but it turns out, so some remarks about the orthogonal complement, that W perp is actually a subspace. So we have W, which is a subspace, and if we take W perp, we again get a subspace. So in this case, when we had a line through the origin, W perp was also a line through the origin in R2. And in R3, when we had a plane through the origin, W perp was a line through the origin. So this is a subspace. We could verify this by just checking the conditions. So remember that that means that 0 is in W perp, that if U and V, if U and V are in W perp, then U plus V is in W perp. And then if U is in W perp and C is a scalar, then C times U is in W perp. Okay, so these are the conditions for being a subspace. Right?
Pardon me.
Yeah.
How does the last one go if UV are in W perp?
And C is in R.
Sorry, the second one, it says then U plus V is, I'm assuming that says also in W perp?
Yeah, I dropped that part because I wanted to write it small. Sorry. So then
Okay,
if
just
U and
checking
V
in.
are U perp, then U and V, U plus V is also. Does that make sense? Okay. So first of all, so we're checking that this is true. First, 0 is orthogonal to everything, so 0 will be orthogonal to W. So we've got that part. If we have U and V in W and V, let's say, right, we'll use, that's fine. And W is any vector in W perp. Then by the definition of W perp, U dot W is equal to 0, and so is V dot W. So that means that if we sum those two things together, we still get 0. And we know by the properties of dot products that this is the same as U plus V dot W. So that means that U plus V, this vector, dotted with a vector in W perp is going to be 0. I think I said that correctly. Right, so we get 0. So that means that U plus V is in, oh wait, what did, I think I wanted it this way. U plus V and W perp, that makes more sense. And W, okay. Then U plus V is in W perp. Okay, and then for scalar multiplication, if let's say V is in W perp and C is in R, then for any W and W, V dot W is equal to 0, and C times that is equal to 0. Okay. Which means that C times V is in W perp. Okay. It's the kernel of so the action of, what do you mean? So what is the action? The dot product. So yeah, I guess you could define to so it's a binary operation, right? So you need to, wait, so you said the action of the vector space on a subspace. So you would have V and W. Into R. V dot W. I mean, yeah. So V W maps to V dot W. And then it would be the kernel of that. I mean, I guess it, yes, that would work, but it's also not that hard to check that it's a subspace too. So, does that answer your question? I mean, I guess. Yeah. Okay, cool. Let's see. So we have that W perp is a subspace. We also get that W perp is just W again, right? Okay, so this is just a definition of, this is a function. Basically, it's like defined using the dot product. And then if you define it this way, then the kernel of the sub, no, it would be, this would be V cross W. So anyways, we don't need to get into this. I'd have to sort this out. I'm not, just ignore this. Okay. We don't need to do this because we just showed like directly that it's a subspace. No worries. Yeah. Okay, so we do have that W perp is equal to W, which kind of makes sense if we look at our pictures. We look at everything perpendicular to W, and then we look at everything perpendicular to W perp, we get back to W, right? So we won't prove that, but that is going to be a property that we can use. Also, if you take the orthogonal complement of Rn, the entire space, right, that will be equal to the 0 vector, because that is the only thing that is orthogonal to everything, right? 0 is orthogonal to any vector, but that doesn't occur for any other vector in Rn. And then also the orthogonal complement of 0, of just the 0 vector, will be the whole space. Right. Okay. Here's another thing. So V is in W perp. So V is orthogonal to everything in W if and only if V is orthogonal to every set, every vector in a spanning set. Right? So that means that if we wanted to check that V is orthogonal to a subspace, we could just check it for the basis vectors, right? And that would be good enough. So we don't have to check for everything. Okay. And then you might have noticed from our examples, but this is the case, that the dimension of W plus the dimension of W perp, maybe I should, okay, first say if W is a subspace of Rn, if, then the dimension of W and the dimension of W perp will add up to the dimension of the whole space. So it'll be n in this case, since we're in Rn. Okay. Okay, so let's see if okay, so this is all of the properties I wanted to mention about WPERP, and let's do an example of actually finding it. So say W is going to be the span of the vector 1, 1, minus 1 in R3. And we want to find WPERP. Okay. So this is what we're looking for. Let's just label that vector. So we'll call it V, V1, 1, minus 1. Okay. And we're looking for all, let's just write this out. We're looking for all vectors. We'll call them X in R3 such that X dot V is equal to 0, right? So let's just write out what that would mean for a vector. So we would have x1, x2, x3 dotted with the vector 1, 1, minus 1, which if we write that out is x1 plus x2 minus x3. So when does this equal 0, right? So we can just think of this as, or we can treat this the way that we usually do for solving the homogeneous equation, right? So we have this equation involving our parameters, I guess you could say. And we move them to one side, we get x1 equals negative x2 plus x3, and x2 and x3 are free. Right? And so a vector x that is in WPERP will have the form x1, x2, x3, where x1 is equal to negative x2 plus x3. And so we can split it. So we get minus 1, 1, 0, and 1, 0, 1. Right? And so we can just write down WPERP as the span of those two vectors. So yeah, this is how we would go about finding WPERP. We can do another example. So say we have W is now, so we'll still be in R3, but W will be the span of, would be the same vector 1, 1, minus 1, and also 1, 1, 1. Right? So now we have, we'll call this one V and this one W, those two vectors. Remember, we want to find WPERP. And we just set up now two equations, right? So we could get, so if X is in WPERP, it will be perpendicular to V and perpendicular to W, or orthogonal to W, so we get these two equations, right? So x dot v would give us the same thing. So we x1 plus x2 minus x3 equals 0. And x dot w would give us x1 plus x2 plus x3 equals 0. And now we have this system of equations, which we can just stick into a matrix, right? So we get 1, 1, minus 1, 1, 1, 1. And we can row reduce this. So we would take row 2 minus row 1, which would give us 0, 0, and
2.
2. Thank you. Okay. Right. And then we can just divide by 2. So 0, 1. And then we can clear.
Wait, there's no.
Oh, what? Oh, sorry. Yeah, okay, I can do this. Right, and then this is finally 0 and 1. There we go. Okay, so we get x1 plus x2 equals 0 and also x3 equals 0. And so this gives us x1 equals negative x2. So our general solution will look like we'll have negative x2 and x2, and x3 will be just 0. So we get this. This is this means that W perp is equal to the span of this vector minus 1, 1, 0. Okay, so we can see that finding W perp is somehow related to finding the null space of a particular matrix, right? So if we were to put these vectors into a matrix, so A was equal to V times D, and V and W as the columns, then here what we're solving is the equation A transpose X equals 0. So it's the null space of A transpose. Right. Okay, so this is sort of related to, well, it exactly has to do with the following theorem. So if A is an M by N matrix, then we have that the orthogonal complement of the row space of A, so if we take the orthogonal complement, that is going to be equal to the null space of A. And let's see. The orthogonal complement of the column space of A is going to be equal to the null space of A transpose, which is what I was referring to up here. So, right, okay, just this one here. Yes, yeah, it's a kernel of the linear transformation associated with A transpose, yeah. So we had this picture a while back when we talked about the row space. So we had the row space of A and the null space of A. These are in the same space. So this would be Rn if we have n by n matrix. I guess I'll do like this. And then we had on the other side in Rm, the column space of A and the null space of A transpose, right? And these sort of partitioned our space into these pieces, right? So we had 2 pieces in Rn and 2 pieces in Rm. And I believe I alluded to this, but we didn't have the definition yet, but these are orthogonal, right? That's what this theorem says. And these are orthogonal. Okay. So for finding W perp, you can just basically create a matrix A with, so if your columns from, we'll say a spanning set of W, right? And then you can just solve the homogeneous equation for A transpose. So you have to first take the transpose and then look at the homogeneous equation. And the null space of that, or, oh, oops. Well, the null space of A transpose is going to be your W perp. Oh my God, okay. There we go. Okay. How are we doing on time? Okay, so we're doing okay. This is okay, everything that we're going to cover in 6.1. So now we're going to move on to 6.2, which talks about orthogonal sets. Okay, so we'll have a definition of an orthogonal set. So a set of vectors so this is going to be a finite set of vectors. So it is just the vectors v1, v2, up to vk, right? So this set of vectors from Rn is an orthogonal set if we have that each pair of vectors is orthogonal. So that means that if we take 2 vectors that are distinct, so let's say the vectors vi and vj, where I does not equal j, so I does not equal j, then these are orthogonal, which means that the dot product is going to be 0 if we take any pair. Obviously, if VI was, if we took VI dotted with itself, this would be non-zero if this was not the 0 vector, right? So that might not be the case, that it's 0. But if you were to take it with any other vector and take the dot product, you would get 0. Oh, is that what I wanted to do? Okay, so not yet. Let me see. So for example, one orthogonal set in Rn is the collection of these coordinate vectors, E1 up to En. Let's see. Each pair is orthogonal. So we have a notion of two vectors being orthogonal, and that means that their dot product is equal to 0. So if we take a pair of vectors, we just check by taking the dot product. If that is 0, then they're orthogonal.
So I guess what I'm trying to ask is, do you have to check if each individual pair is orthogonal?
Yes, according to this definition. So it's sort of saying that if you were to take any pair, then it would be orthogonal.
Wait, it would be?
If it is an orthogonal set.
Okay, and this is an if and only if situation. So if you check each pair and each combination of two vectors is orthogonal, then it's an orthogonal set?
Yes, yeah.
Okay, thank you.
Yeah, no problem. So if you have any two vectors in this set of these coordinate vectors, if I does not equal j, that means that ei dot ej, what you get is some, I'll just assume that they're like, this is the ith coordinate and dotted with the jth coordinate. So this is hard to express, but we know that those, that one entry that is non-zero is going to be different if I is not equal to j, right? So we're going to get always that the dot product of those is 0. Does it make sense what I've, so ones occur,
At different positions.
yeah.
So that means like when you multiply the corresponding entries, one of them will always be 0.
Yeah. Yeah. So yeah, you'll always have a 0 times something, which will give you 0. And then when you add all those up, you get 0. Okay. And then we could see the following. So if we have the collection U1, U2, and U3, where we'll define what those are going to be. So U1 is going to be 101. U2 is going to be -141. And U3 is going to be 2, 1, -2. And I claim that this is also an orthogonal set. And we could check this by just taking the I should write an orthogonal set. Just taking the dot products, right? So u1 dot u2, we can look at that. That would give us -1 plus 0 plus 1, so that's 0. u1 dot u3 would give us 2 times 2 plus 0 plus -2, so -2, which is also 0. And then u2 dot u3 is equal to -2 plus 4 minus 2, which is 0. Okay. So those are all of the possible combinations, because if we were to do this in a different order, we would just get the same thing, right? By the properties of dot product. So yes, it is orthogonal. Okay. So we have the following theorem, which is pretty nice. So if you have that u1, u2 up to uk, if this collection is orthogonal, maybe we'll write it as a set. So if this set is orthogonal, then these are linearly independent and non-zero. Or maybe I'll put it this way: does not contain the zero vector. Then the collection is linearly independent. Which I think kind of makes sense from what we know intuitively about linear independence. For instance, if two vectors in R2 are going to be linearly dependent, they have to be constant multiples of one another. So clearly, if we had a right angle between them, that couldn't happen, right? So if these were orthogonal, they would be linearly independent.
But that would mean the converse of the statement is not true, just because like if the set of vectors are linearly independent, they're not necessarily orthogonal.
Yeah, so that it would not be the case that if they're linearly independent, they're not necessarily orthogonal. Right? So maybe linearly independent does not imply orthogonal. For example, if we took the set 1, 0, 1, 1, these are linearly independent, but not orthogonal because their dot product will be 1. Right. So you can double check that this has those properties. But let's go ahead and prove this theorem. So say we have this set right here, so u1 up to uk, and we want to look at that linear combination of these vectors. So c1, so we have coefficients. Oh, I guess we're using k. CK times UK is equal to 0. Okay, so we want to show that these vectors are linearly independent. So we want to show that we have to have that C1 up to CK, all of these are equal to 0, right? Okay, so what we can do is take our equation and dot it with U1 on both sides. So dot this whole thing. Equals U1 dot 0. Now we know that any vector dotted with 0 is going to give us 0, right? And then we're going to use our properties of dot products to allow us to distribute this guy in, right? So we would get C1 U1 dot U1 plus C2 U2 dot U1 dot U2. CK U1 dot UK. Right. Okay. Now U1 will be orthogonal to each of the other vectors, right? So that means that this is going to give us 0, and all of the other entries there are going to be 0 because U1 is orthogonal to each of them. But U1 is not orthogonal to itself, right? So this is not going to be 0. In fact, if U1 is not equal to 0, this is going to be some non-zero number, right? So what do we get? We get C times U1, or we could just write it as the norm of U1 squared is equal to 0. So since U1 is not the 0 vector, the norm of U1 is not equal to 0, so we must have that C1 is equal to 0. Right? And then we could just do this trick with U2 and then U3 and then all the way up to UK. So we do the same thing with U2, U3 up to UK to get that all of those constants are equal to 0, which means that we have linear independence. Okay, I guess we're out of time. Okay. Any questions right now, or?
No, not at this moment.
Okay, cool. So yeah, we will continue on with this section next time. And I think we will have one more quiz. So I'll have a quiz on Thursday. That will be our last quiz of the semester. And also your exams are graded. So if you haven't yet seen your exam, you can take a look at that on Canvas. What will the quiz be on? I don't know because it's been a while since we've had a quiz, so I will post it on Canvas. Maybe I'll send out an announcement about the quiz topic later today.